Okay, let's get into some of the actual routing strategies here. So here's an example of what we call proactive routing. And you can read the details in the paper. I'll spare you the details of this, but the notion of proactive routing is where we're making decisions in advance of any entanglement being generated. Okay, so we're deciding on the paths before we flip the switch and turn on the network. This requires global knowledge of the network. We need to know the global physical topology, how are things connected and hooked up to each other. This all needs to be known to some kind of central controller. This could also be distributed across nodes, so different ways of doing this proactively. But the notion is that we're making routing decisions before any operations are actually being done. Alternatively, an approach to routing is more reactive, or sometimes called dynamic routing. And here the idea is the routing entity is actually reacting to the state of the network. And this is really where I think the difference between classical networking and quantum networking shines. A lot of classical routing technologies are very what we call stateless. They don't necessarily depend on network state too much. But in quantum networking, that's not the case. Reactive routing, it's very, very stateful. So we're deciding on paths and schedules and swaps in reaction to the virtual state of the network, right? So every once in a while, the network will report, hey, here's the state of my network. Here are the entanglements I have. Decide what you want to do with it. And so that's what you can consider reactive routing. This could be great in certain scenarios where because we're kind of dynamically reacting to like the real-time state of the network, we can more effectively use resources and protocols. However, we're dealing with very short lifetimes here, so this would need to happen in a very fast process. There are pros and cons with all of these different routing strategies. Virtual routing. So the notion here is that you have a physical topology. These are the physical wires that connect things. But as we're generating and distributing entangled pairs, you can kind of think of this virtual or logical topology that is abstracted away from the physical one. And so we have these virtual links. For example, here, that green line is a 3-hop entanglement. This is a virtual link that exists. It's a quantum link that exists. And so with virtual routing, we can specify the virtual links we want to generate, or we can react to the virtual links that have been generated and begin to kind of stitch them together with swapping to meet a certain user pair path. Okay. The thing here is that each virtual link can only be used once, right? So it's an entangled pair, this virtual link. And as soon as that pair is consumed, either for swapping or for something else, then it's gone. We need to regenerate if we want that virtual link again. Whereas, a physical connection can be, of course, reused indefinitely. Opportunistic routing is a way in which we kind of build up the path as we go from source to destination, or from one end node to the other, and hop by hop kind of make decisions on where the next hop will be. So this is a way to kind of like build up unidirectionally, or sometimes bidirectionally as well. The nice thing about this is there is no preliminary or proactive path selection before things happen. And this is kind of in reaction to, local state. So how do we decide on the next hop? It depends on what's going on in the current state of the network. So it's kind of an opportunistic approach. So there's kind of 4 examples of the routing strategies. There are more that we considered and that you can see in the taxonomy. One thing I did want to mention is that these are not mutually exclusive. They can be combined.